So let's go ahead and finish our work on section 1.2. We're going to work through the example that we put on the board at the end of class. We want to find the general solution to a system of equations. The system actually has 6 variables and 4 equations. So a solution would be a value for x1, x2, x3, x4, x5, and x6. A solution would consist of 6 different numbers, right? And we already had set up the augmented matrix, so here it is. And we're going to work on that matrix to find our general solution. There are 2 steps to this problem. The first step involves reducing the matrix to its reduced row echelon form. And that's a process we've gone through several times now, so you might skip ahead if you're really comfortable with that, even though there are some other unusual little quirks to this that we haven't quite seen before, so you might benefit from seeing the steps also. The second part of the solution is about how we interpret the reduced matrix. The reduced matrix itself is not our answer. We have to turn that back into a statement about the variables involved in this equation. So the end of the video is very important because we haven't talked about how we interpret the reduced matrix yet in class. Also, this is a pretty complicated, messy problem, and I chose this one on purpose because I actually think it's a lot easier to see what's going on from a problem that has lots of variables in it than from one that only has a few variables. Let's go ahead and start. So I can see I already have a 1 in the upper left-hand corner, my pivot position, so that 1 is just what I want. I'm going to leave the first row alone, but I now want zeros below, so I'm going to change row 2 and I'm going to change row 4. Row 3 already has a 0, so that's good. So row 2 I'm going to replace with row 2. Let's see, there's a 2 here, so I want to take 2 minus 2 times row 1. R2 minus 2 times R1. For row 4, I'm going to replace it with row 4. I just noticed I have a mistake here. I want 1, 2, 0, 2 in this position. Sorry, I just recopied that one incorrectly. So row 4, I have to replace with row 4 minus 2 times row 1 also. Okay, so let's go ahead and do that calculation. So 1, 3, negative 2, 0, 2, 0, 0 stays the same. Now I'm going to change row 2. 2 minus 2 times 1 is 0. 6 minus 2 times 3 is 6 minus 6 is 0. Negative 5 minus 2 times negative 2 is negative 5 plus 4 is negative 1. Negative 2 minus 2 times 0 is negative 2. 4 minus 2 times 2 is 0. Negative 3 minus 2 times 0 is negative 3. And negative 1 minus 2 times 0 is negative 1. And now I recopy 0, 0, 5, 10, 0, 15, 5. And let's work on the 4th row. Again, that's got to be a 2 because that's the coefficient of x1 in the last equation. 2 minus 2 times 1 is 0. 6 minus 2 times 3 is 0. 0 minus 2 times negative 2 is going to be 4. 8 minus 2 times 0 is 8. 4 minus 2 times 2 is 0. 18 minus 2 times 0 is 18. 6 minus 2 times 0 is 6. So I now have this. And my first column now is set up as a pivot column, 1 on top, 0s below. I look at the second row now, and I move left to right until I get to a non-zero entry. That's this -1. That's going to be my pivot position. And so I'm going to change, I want to change row 2 by just multiplying by -1 to change it to a +1. So row 2 will be changed to negative row 2. 1, 3, -2, 0, 2, 0, 0. Now I multiply through by -1. 0, 0, 1, 2, 0, 3, 1. Recopy 0, 0, 5, 10, 0, 15, 5, 0, 0, 4, 8, 0, 18, 6. So I have my pivot position here, pivot position here. Below the 1 now, I'm looking down below the 1. I want zeros below in this third column, so I want the 5 to change to a 0 and the 4 to change to a 0. So I will change row 3 to row 3. Well, I would take this, I want to take this 5 and subtract 5. So I'm going to subtract 5 times row 2. And row 4 I'm going to replace with row 4 minus 4 times row 2. And let's calculate the result of that. I'm recopying the first 2 rows. And now, row 3 minus 5 times row 2. 0 minus 5 times 0 is 0. 0 minus 5 times 0 is 0. 5 minus 5 is 0. 10 minus 2 times 5 is 10 minus 10 is 0. 0 minus 0 here. 15 minus 5 times 3 is 15 minus 15 is 0. 5 minus 5 times 1 is 0. And yes, I got a row of zeros out of this process here. Now let's do the row 4 calculation. 0 minus 4 times 0 is 0. 0 minus 0, 0. 4 minus 4 times 1 is 0. 8 minus 4 times 2 is 8 minus 8 is 0. I'll have a 0 minus 0. 18 minus 4 times 3 is 18 minus 12 is 6. 6 minus 4 times 1 is 6 minus 4 is 2. Okay, so that's the current state of things. Now because I have this row of zeros here in row 3, we always want our 0 rows at the bottom. That's something we haven't seen yet in one of these reductions. So to put my 0 row on the bottom, I'm going to interchange row 3 and row 4. So no calculation, just shifting things around. 1, 0. They're both zeros here. 3, maybe I better go across because I'm not changing the first 2 rows. And now I'm going to put row 4 in the third row. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 6, 2. And row 3 ends up on the bottom, all zeros. So not much going on there, but I have zeros on the bottom. I have my first pivot position, second pivot position. Now I'm going to go across what is now the third row over to this 6. Oh, sorry, I did that again. Went off the bottom of the screen. And this 6 I want to be a 1. So I'm going to replace row 3 with 1/6 times row 3 to get a 1 in that position. And I'll go ahead and copy that onto another sheet. 3, negative 2, 0, 2, 0, 0, 0, 0, 1, 2, 0, 3, 1. And taking 1, 6 now, 0, 0, 0, 0, 0, 1. 1/6 of 2 is 1/3. 0, 0, 0, 0, 0, 0, 0. Okay, so at this point I have my matrix in row echelon form. What I want to do is get into reduced row echelon form at this point, correct? And so I'm going to now start the backward phase. Let's maybe just mark our pivot positions. So in the backward phase, I'm going to start at the rightmost pivot position, and I want to get zeros up above. And then I'm going to get zeros up above this guy. And of course, there's no zeros up above the third pivot position. So up above this one here in the last pivot position, I really only have this 3 I have to get rid of because I already have a 0 in the first row up above. So I want to change row 2. And I'm going to take row 2 minus, again, I'm going to use the row with the pivot in it to help me change the value I want to change. So row 2, I'm going to subtract 3 times row 3. Negative 2, 0, 2, 0, 0, 0, 0. All right. See, row 2, I'm now changing. I'm taking row 2 minus 3 times row 3. So 1 minus 3 times 0 is 1. 2 minus 3 times 0 is 2. 0 minus 0. 3 minus 3 times 1 is going to be 0. That's what I'm trying to accomplish here. And 1 minus 3 times a third, 1 minus 1 is 0, I believe, right? Then I have 0, 0, 0, 0, 0, 1, 1/3 in my row of zeros. Okay, so we now are good above and below. We have zeros above and below the 1, the third pivot position. In this second pivot position, we need to get a 0 up above. So I need to change row 1. I'm going to replace row 1 with row 1 plus 2 times row 2 in order to change that negative 2 to a 0. And then we'll have our reduced matrix. All right, so I'm changing row 1 plus 2 times row 2. So 1 plus 2 times 0 is 1, doesn't change. 3 plus 2 times 0 doesn't change. Negative 2 plus 2 times 1 becomes 0. And now I should be careful here. Row 1 plus 2 times row 2. So I have 0 plus 2 times 2 is actually going to be 4. And I have 2 plus 2 times 0 will stay 2. 0 plus 2 times 0, 0 plus 2 times 0. So I think I have 1, 3, 0, 4, 2, 0, 0. 0, 0, 1, 2, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1/3, and a row of zeros. Okay, so we actually have our matrix now in reduced row echelon form. But what is this telling us? This is the important part of this example now. How do we interpret what we've just found out? Well, every matrix along the way in this process corresponds to an equivalent system of equations in the original variables. The variables were x1, x2, x3, x4, x5, and x6. And each of those first 6 columns correspond to coefficients of those variables. Remember, the last column in the augmented matrix corresponds to the constants on the other side of the equations. So I'm going to write the equations that we have now. We have gotten to this point. We have x1 plus 3x2 plus 4x4 plus 2x5 equals 0. Okay? And we also have x3 plus 2x4 equals 0. We also have x6 equals 1/3. And our last row of zeros corresponds to just saying 0 equals 0 with no variables involved. Now, is this system consistent or inconsistent? Does it have a solution or not? The only way we could end up with no solution is if we have an equation that we saw in an earlier example where you have 0 equals a non-zero number, like 0 equals 5, 0 equals -3. That would correspond to a row that's almost all zeros except for the last entry. We don't have that here. We have 0 equals 0 is fine. So this is a consistent system. There are solutions. There is a solution. And we also saw an example where there was exactly one solution, and that will always be very obvious because you'll have each variable equal to a constant. Here we only have x6 equal to a constant. The other variables are still buried in the equation, or equations that relate them to each other. So this is consistent. There are solutions. But we are not in a situation where there is just one solution. We are actually in a situation where there are infinitely many solutions. And we need to try to describe those solutions. And what's going to help us is a couple words we're going to attach to the variables that we use. And let me just write it this way. Pivot columns correspond to basic variables. And let's see, my pivot columns are, here's a pivot, here's a pivot, here's a pivot. So my pivot columns are the first, the third, and the sixth. So the basic variables here we're going to say are x1, x3, and x6. x1, x3, and x6. The non-pivot columns correspond to what are called free variables. And it's really helpful to see the distinction between these two. So the non-pivot columns are second, fourth, and fifth. So free variables are x2, x4, and x5, x2, x4, and x5. Now let's express the general solution to this system. That's really what our answer is going to be, what the general solution is. The general solution means we're saying what x1, x2, x3, x4, x5, and x6 have to be equal to. All right, so the general solution we want our variables lined up in this way. Each of the basic variables can be expressed in terms of the free variables. So what we're going to do is for each basic variable, like x1, we're going to take an equation and isolate it. X1, if we isolate it, is equal to -3x2 minus 4x4 minus 2x5. x3 is equal to negative 2x4 when we isolate it. And x6, it's actually equal to a constant. It's already isolated, and it has to be 1/3. It's, doesn't involve the other variables at all. So notice x1 and x3 are both expressed using free variables, x2, 4, and 5. For 2, 4, and 5, because they're free, we just say is free. Is free. Is free. And that's what our answer is going to look like. Let's just talk about it for a second. What we're saying is a solution to this system consists of values of each of the 6 variables. You could pick any real number to be a value for x2, any number for 4, any number for x5. But once you choose those three values determine the values of the other 3 variables. Well, x6 is always 1/3. So the free variables can be any number. The basic variables depend on the free variables. And we'll talk more about how to interpret this geometrically in a later section, but right now we're through with this example.